Good afternoon and welcome to this presentation about best practice to run Percona operator from MySQL, which is an extension of my previous presentation, MySQL on Kubernetes Demystified. I'm Marco Tusa, and I will be your host for today. And if you see this, unfortunately, this means that I still have COVID or have been identified as positive to COVID, so I cannot attend directly and personally the Percona Live event. So I'm preparing this video in that unfortunate case. What we are going to talk, first of all, is the why this presentation, and a little bit a look at the past, what happened before, what is our history, and what the benefit eventually of using the approach that Kubernetes and containerization brings. And then we'll do a reality check about what is what we wish and what is for what we have in front of us as a real scenario. Finally, I will give you some hints about architecture and setting up, and about the backup and about the pods, or setuping, and small hint here and there in general. Finally, my conclusion. Anyhow, so why this presentation? There are many voices around using MySQL or relational database in general on Kubernetes, but that is something that is a dangerous generalization, because what we need to be careful of is to understand what we are doing in terms of relational database, which means understanding the relational database model. And we need to see exactly what is that for, and when this apply well, and when this doesn't really fit in, okay? So to understand that, the first thing we have to do is look at the past. And look at the past means look at when the relational database model starts, or when at least I want to start from when I start using it, okay? And when I start using it, it was a long time ago, in 1987. And at the time, that were here is the list of the available databases. If you can see, we have only probably one of the most used database today, right? Which is Oracle. I don't think even that we still have, yeah, it's mainly Oracle, and then in large corporation there was Ingress, there was a Informix system, and so on and so forth, but there were not at the time, of course, Postgres, which actually came up 1 year later, if I remember correctly, or MySQL that comes much later on. But why? Well, if we go back to that time, the point is that the server were the database was based on a single server. It was having connection from clients that were connecting directly, and that was that means that normally what was happening is that one database server was serving few connections, serving few connections that were actually open and kept open for probably a long time, and the interaction was happening in a very limited and very well established way, and the application were able to connect, but not to open thousands of connection in a few seconds. Then the internet comes, and a lot of the game changed a lot. A lot of new applications were built, and of course some of them were looking for data on simple files, or we were looking for data on well, actually also text files, CSV files, and then there were applications that were instead looking at more complex database structure and relational data. But the important thing here is that the applications start to serve hundreds, thousands of different users. And because through the web, you cannot easily limit the number of connection or requests you can have. Once you are out there, you are open to the world. And that brings the application to a significant restructuring. We see the application to become a little bit more flexible and extendable. They need to change. And we start to have different layers that well-defined, that needs to be isolated as much as possible in order to serve the what are the use in a more agile way, in a more as I said, flexible way. And so the service-oriented architecture come up. And that model was largely adopted for many years. Then what happened again is another evolution. That was not enough. That application needs to serve so large, so many customers, so large plateau of customers that at the end, they need to scale in a different way. It cannot be not monolithic in one server. It needs to be splittable. And that splittable was the evolution, right? The application start to be modular, and you have service, a microservice that can be put in different nodes, and the nodes can look at can be looked at in different nodes, and the nodes talk to each other, so they can eventually exchange data and can eventually be replaced and evolved independently, which of course brings us to also crazy structure. This is actually from 2008. It is the AWS microservice scenario. And, you know, I just compare with the Dead Stars from 1977. But yeah, that is reality, and is reality from 14 years ago. I don't even, I can't imagine what it is right now, today. Probably a nebula or something like that. And but that was the application side. And what happened to the database? Well, keep in mind that we start from a single server that was serving, you know, the applications that were connecting, and at the time it was more the client were in 101. But what happened to the database servers? Well, actually, nothing. The relational database remain more or less the same brick. They stay like that by design because they need to keep consistency, right? And there are several rules and limits that force the brick to remain a brick. Well, actually not true. We had several bricks, which we call clusters. And we use them for high availability. And we also pretend them to be, you know, in some case, scalable. And they are not. But this is something that we will see later on. Anyhow, all this different modularity brings benefit, right, from the application. Of course, they brings benefit in terms of you can have modular a modular approach. You can have a different process from by module, for development, for testing, and of course the fact that you can have high number of nodes serving the same function, you have higher resiliency. They scale better because instead having just one single application node serving the functions, you can have multiple and nodes serving the same function, so you can extend the number of connections that you serve at the same time. As I said, better fault tolerant, better fault isolation, more resilient application. Then you can have integration to legacy systems that are actually served by a service, so by a module. So you don't have to transform everything. You just have to create a module that actually interact with that application, and you will have what you need, and so on and so forth. I mean, there are so many benefits, and we all know them. But again, what about the databases? Well, that is a little bit different because the modularity, for instance, you need to understand the data when you talk about modularity. And And for a database, we can identify mainly two different way of doing of considering modularity. One is for service, and the other one is by context. So what is it? By service is when you use, for instance, a login, right? So an application that manages logins just needs the information about the user, the password, the token, the two-factor authentication. That's it, right? And at database level, this is okay. Give me username, location if it's relevant. Of course, the password is relevant, the token if it's relevant, and that's it. So specific segment of data. And or by context. The other way you can have modularity is by context. An example is when you have multi-tenant database and application, then you need to split that set of data, keeping the integrity of the definition, but you just separate the data. So I have I don't know, a system that manages multiple shops. Well, I have to split by shop and keep the same schema definition. And of course, the scalability here is limited because in order to have a scalability, which normally you can obtain with the by service approach, you need to have a system that in the database, for the database, that is able to have a distributed locking that is not actually impacting the performance, that is not causing the other nodes to block the data, block serving the data. Or you must be able to shard, which is an extension, as I said, of the the context way. Of course, this is when you start to split, you have a better fault isolation because you have different blocks and different elements that works independently. So if one segment fail, only that segment will fail. So if you have a login module that is duplicated in multiple situations, then only that specific segment will be down, while which means that maybe just few users will be affected, right? Or and if you, for instance, instead will go for model by context, you will have just one shop affected by that, not everything. I don't really see that working, the integration, unless if you use the service approach. Otherwise, you have to deal with the same kind of structure, and of course, you will have a better, faster time to market if you use the by service approach, but not by context, because actually with by context, you will have to apply the same change to the schema multiple times. So if you have right now have all the shops in one server, once you have that done an alter on a table done, you now have to do the alter on the table for that specific table on all the different shards that you have. So it's a little bit more impacting, to be honest. And this brings us to, yeah, there are benefits, but what is for real? What is really the situation here? So this is a very simple scenario. And actually, this scenario is a simplification of what we see every single day, right? We have multiple database that are, multiple applications that connect to one database. And those different services are different microservice specialized. So one is login, the other is the catalog. And all of them at the end are querying the same database, the same server, the same structure. What I mean for the same structure, here we go. I mean, this is an example of schema, and you can see that the relation that each table has with the others, and that is the base of a relational database. When data needs to be kept in a table that have some rules that define what can be in and what cannot be in terms of data integrity itself. So you cannot have, for instance, an order without having, in this case, I don't know, let's say an order cannot be without order items, or an order items cannot be exist without an existing order, right? Or you may not have a user without an order without a user that actually is doing the order. So it is something that we need to be aware of when we actually talk about modularity, because that is the key. So when we talk about the context modularity, we talk about having the possibility to split the data in chunks that are consistent, like one single shop that is going to be consistent because it's going to work independently by another shop. So we can easily do it without any problem in separate that in its own shard. And that is okay. We just need to have eventually manage that part. In terms of scalability, we have another point here. If you create a single tenant part, I mean, so a single shop, then you have an additional need of scaling this shop. Now, the implementation that currently exists for Kubernetes and containerization that are based on standard MySQL are, the Percona XRDB cluster, PXE, or there is a solution with MySQL that are doing their operator as well. There is it will come that also a solution in Percona with group replication, and there is already in alpha another solution using asynchronous replication. But the point is that both PXE or group replication use, also if they have multiple writers, in theory, they at the end approach that is a single primary. So also, if you are using the multi-primary as a concept, you cannot really use the multi-primary in reality, because it will not give you any scaling writing, actually, because the mechanism of checking the different writes incoming, you will slow down the process. You will not get any benefit. And of course, if you use a solution based on simple Percona server, which is standard asynchronous replication, you have one single primary at time, right? So what is the level of scalability that we can achieve here? Mainly known. We cannot scale above the capacity that the single pod has. So you can scale up in terms of giving more resources, memory, CPU, but that will not help you in the sense that it will not give you additional scaling capacity as we have for in the application. So as mentioned multiple times, the only way is sharding as much as you can. So if you shard, you have another set of problems here. Then is how to shard, right? So let's say that we already have decided to go for an approach that where the shop is splitted by single shop. So you from multi-tenant to single tenant, and then you have your shop working isolated. Then you need to increase the scalability. You want to shard. Now at this point, the application needs to be. You have mainly three choices, which well, let's say the first one is the having the application be fully aware of what kind of sharding mechanism, what kind of shards you have, so the application decide where to point in terms of IP, where to go, or entry point where to go. And and that is not really flexible, right? It's not really good because then you need to bound everything at the application level. The other one is to have a generalized catalog that actually manage the different shards, and the application needs to read the catalog, and then it will be eventually redirecting the functionality. Or the last one, that is the one that is less impacting application wise, and also the one that we have seen more used recently, is the where the application injects something in the request that is passing to eventually another mechanism that we will see, that reads that information and decide where the query needs to go. This brings us to an architecture like this, where you have all the applications that are pointing to, well, I put here a single proxy SQL, but that could be actually located, actually should be located in same closer to the application service. So, but you connect there, and the application injects some information, like I'm a shop and I'm doing an order, and this order is for the regional geographic regional, I don't know, Europe, right? And you have sharded your shop by geographic region. So you have one for North America, East, Central, West, Europe, East, West, South, whatever, right? And then you can have your application just injecting the information of which geographic area is serving, and that could be, again, something that you do by in the microservice, because that's more manageable. And then your request is redirected. In that case, you have the scalability, you have the chance to increase your scalability, as I said, sharding and distributing the request. But that's the only way for the moment. But this brings another problem, right? This brings another problem. The fact that there is not only the problem about scaling, there is also the problem about the service itself. In order to keep the service on Kubernetes, on containers, efficient, given the fact that the mechanism that is used in Kubernetes is to provide and ensure the service, you may incur in some pods that are composing the services that are actually killed, or that needs to be restarted or needs to be rebuilt, and that will actually put the cluster in a degraded state, right? If you lose a node that is providing the service, you will continue to have the service also with one node, but your capacity of serving, for instance, reads, will decrease, right? So what you want to do is always to have the maximum number of nodes in order to serve the writes only with the primary, but the reads with most node possible. So the point here is, in order to have an agile system, you need to be careful about the dimension of the data set that you have. So if you think to, for instance, move a system that you currently have of 40 terabytes of data. 40 terabytes of data is nothing right now. Well, nowadays, it's nothing. It's really something that you can find very commonly around us. But when you move the 40 terabytes in a system like with Kubernetes and with the operator, that will become a problem, not when you serve and when you run, but when the pod needs to be manipulated or it needs to be rebuilt, because the amount of time to rebuild the pod will be very long, and your cluster will stay for a very long time in a deprecated state. So the way to fix this is to be aware of what is your live set data and what is instead your data that can be archived. But archive doesn't mean that you are putting away. The archive means that you are actually moving your data in a system, data warehouse system, that is able to serve your request in an efficient way, probably more efficient than what you have with a OLTP system, and it's still online. So at the end, what happened is that you need to build the situation as we were having before, plus an additional layer that is actually extracting the data from each pod, from each shard, and push the data to the data warehouse. At this point, you will be able to serve, continue to serve your shop online with real-time data. Plus, if you need to do, tell me all the orders that I have done in the last 2 years, you will have a data warehouse system that will allow you to mainly include serve the data that you have from the past, plus eventually, the most recent data that you have pushed. And at the same time, you will keep your data set on the pods small, such that it will be very fast and very easy for the mechanism to rebuild the node if there is any problem. So the other approach, as we were talking at the beginning, is modularity by service. So in this case, what we do is just to keep what we need. I just need to have, a small system for the orders. So I don't have to keep all the schema that is around it. But if you can do that, if you actually use just a small segment, then this means that all the foreign key, all the reference that you have to the other table will not be there any longer, will not be active, will not check the data. And that could be fine, because you may have all this logic built in the application. Fine. Which means in this case, you don't need a relational database. That if you can do that, if you are able to go in that direction, just go and do not use, for instance, Oracle or MySQL or Postgres, because they are relational database and they will limit you too much. There are other products that could serve you better. Then there is another reason for which a lot of our customers are looking to containers and Kubernetes and operators, and those are this reason is mainly the simplify the operations, and that makes a lot of sense because, for instance, if you use the Percona operator for MySQL, you will have a lot of operation like installation, the possibility to build a DR site, so geographic distribution, the backup and restore, point-in-time record, all done automatically. So it will just mainly how you configure your operator, and then you launch it, and it will do all that for you. That's amazing, right? Of course. And also for management, that will be easier because you just need to replace in one file and it will be done all on for the whole cluster. And plus, you can also optimize the use of your resources. What it does mean? It means that you can have we can take, for instance, a large EC2 machine and put multiple cluster on it, and based on the level of utilization that each cluster has, combine them and optimize in an easier way than using virtual machines the utilization of the box itself, so more value for money. However, as I said, large set, may suffer of significant impact. And then you need to keep in mind the discussion we were having before. Sorry. And not only under heavy load, the node pods, the pods will become a lot busy, right? So you need to be very careful because when they are busy, the Kubernetes system and has a mechanism to analyze the health of the pod, and that could become a little bit tricky to identify, okay, I'm not getting the right answer or the answer in the right amount of time because something is going wrong or because the node is busy. So that part needs to be work and tune on in time. You know, we cannot just come out of the box. It needs to be on your based on your specific workload. And as we said, there are operations that require a rebuild of the pod. So it is pivotal from one side to tune correctly the different liveness, and that we will see later on different parameters. But at the same time, it is very important to keep the data that you are using small as small as possible in order to facilitate this rebuilding process. And always start small, which means use the applications that are busy enough but not too much, critical, well, production but not critical, you know, so such that you start to use the tools and you start to learn on things that are manageable. So let's see what kind of possible architecture we can use. The simpler one is this one, you know, having multiple application microservice or multiple application, whatever you want, using an entry point, which I highlight as Azure proxy, and then, you know, having the pods, which is the cluster, the pods serving. In this case, we will have a single primary writer, which will actually be able to serve enough the applications, and that's it. I mean, very simple and nothing very complex. Or you can have a little bit more complex situation where you build a disaster recovery site and you start to have, you know, enable the backup that of your data. Actually, you should do all the time, and then the data is then pushed to an external bucket, an S3 bucket, and you can you know, then take the backup and process it in order to do restore, verification, and so on and so forth. And of course, the geographic distribution is built, you know, again from the asynchronous using asynchronous replication directly from the operator, which is extremely helpful. It is also very interesting to use the asynchronous replication with the mechanism that is making auto failover when one of the nodes in the pool, so one of the pod failed, such that the asynchronous replication channel will be rebuilt automatically using a different pod, and that is again all managed by the operator automatically. And finally, our complex scenario, which I didn't add the geographic replication here, but you can have it the same level of mechanism and the same level of DR that you were having on the previous slide. Here, the difference is that you use not the application in terms of your multiple service, that you use, a proxy SQL attached to each application, and from that you shard on this, you send the data and you read the data from different shards, and then you have the mechanism to collect the data, you have the mechanism to extract the information and save everything in the data warehouse and performing backup. Now, what kind of settings we need to be careful? we need to be aware of, and we should put some special care. Well, let's start with the node. The node is the main element, right? Is the machine. Let's put it in this way: is the machine where you are going to have the your pods running. So first of all, always dimension the node to host multiple cluster, and otherwise you will mainly do relation one-on-one. So go for the service directly. I mean, you're just using an additional layer that could be only creating problems. So don't do it. Try to optimize the resource for multiple cluster. Is a cost-benefit balancing, right? Then always use that you are allocating your nodes in a different and multiple availability zone. This is normally done for you by the automation in AKS or GKE, but just be aware of that. If you customize cloud, that you need to have the nodes in different availability zone with a very strong network, very high performance network, because of course what is going to happen is that your nodes need to talk, and when your pods needs to talk, they are on the node. So the nodes needs to talk, the pods needs to talk, then the other pods needs to talk. You will have a very high level of network utilization, and that could be extremely heavy and create significant penalty, which means that if you do not have a high performance network certified, guaranteed, you will have you may incur in a lot of problem when you have the moment of high load on for your business, and being in trouble just for that. The last thing that is at node level, you need to be very careful. Of course, the RAM and is coming with the dimension of the node, but is the level of the storage. Always use an SSD with high number of IOs. Normally, not below 3,000 IO per second. That is the below limit. By default, almost everyone gives you just the basic storage level. That's not, by far, is not good enough. So you need to extend the storage class. For instance, in this case, I was just adding, the IO1, and as you can see, the default is GP2, and that's absolutely not good enough. Then the second level is the pod. Now, as discussed before, in the pod, you have the possibility to instruct Kubernetes to check the pod at regular time to see if everything is running correctly. And of course, you can also set the resources. Now, by default, the operators come with very low level of resources. And this is on purpose, because that needs to be changed by you in order to be adapted to your specific usage. The defaults are for your testing, just a dummy check, see that how things are working, but not good enough for a real, let's say, development environment, or for a real staging environment. Absolutely, or not even think about production. So the first thing you should do is to tune your memory. And this is very, very important, because what you need to do is to calculate in MySQL all the memory that you are utilizing for the buffers, for global buffers, and per connection buffer, and in this case also for InnoDB buffer pool, and eventually for the Gcache, the Galera cache. Be very careful in this calculation. Why? Because if you do not calculate correctly, and it's better to be conservative than permissive. If you exceed the amount of memory that you give at pod level, if you exceed the amount of memory at MySQL level, that will generate an OM kill, which means that your pod will be killed because the service will be, is actually going beyond. It's trying to eat additional memory, and it will be chopped down. So be very careful. There is no way to prevent this as a safeguard mechanism. So be very careful. Be diligent. Do your calculation, and again, start small. And then, if you see you can expand, increase the memory while you're doing, your different buffer for join buffer or the temporary table or sort or whatever, and the buffer pool itself. So and this is very important. The other important thing is that by default, the checks for readiness, for liveness comes with very low limits, and they are okay. Yeah, they're fine if you are not having a lot of traffic. But if your pods are working and working hard, they may not be able to answer in that time frame. And maybe the cluster is perfectly healthy. It's just very, very busy. It's just taking its time to do other important things than answering, hey, yeah, I'm okay, I'm okay, I'm okay. Just serving your data. So yeah, it may take a little bit longer for Kubernetes to realize when something is wrong, but at least something is wrong for real and not just because I'm busy working, right? So I suggest you to to increase the value of readiness and aliveness to something higher, significantly higher. I have been doing this test, and at the end, I saw that it is normally good to increase to 4 minutes or even more, but I can tell you that sometimes you have a perfectly healthy cluster that is killed by a response time that is taking more than 10 seconds or 1 minute. I know it's long, but that happened. The other element that I want to cover here is the HAProxy. HAProxy is the standard way to access from external the data. HAProxy, we have two different entry points. One is for write, one is for reads, and it offers exactly the same thing that we have for the pods. When it's not busy, 1 second timeout is okay. 5 seconds timeout is okay. But when it's busy, that's a little bit too short, right? So increase a little bit, like 30 seconds, 60 seconds. It works fine. And it gives you, I understand. It takes longer to be recognized, perfect. But at least when it's working, it's working. It is not chopped down because just busy. The other interesting part is that in HAProxy, you can, through the configuration file, you can pass almost all the different configuration parameters, except for the backend information that are built by the operator, and those information are eventually modifiable in a different file. We'll check later on. But what is important here is that you can really modify your HAProxy and set it as you like, at the best way that you want. You can set all the different parameters directly. But if you need to change the backend, like if the connection timeout, or if you want to change the time of the check interaction, the check loop, or the if the attempt to rise or fall, then you need to modify another file that is called my env var secrets, This is also in base64, so it needs to be obscured by using base64, and then you can modify also that segment of the backend file. So the operator will read this file and will cache it, then will use it. I was talking about ProxySQL, and there is an option to enable ProxySQL in the operator. Personally, I don't like it. I don't recommend to use ProxySQL in the operator, inside the operator. I prefer to use ProxySQL close to the application, because in that way I can have a better modularity. I can eventually manage, have a different approach in terms of connectivity. I connect locally to my ProxySQL, which is much more efficient. I can eventually cache the data at my ProxySQL level, which is incredibly efficient. I can eventually use sharding that otherwise I will be in trouble to use if I use ProxySQL inside the operator. I can use filtering, I can use firewalling, I can use a lot of things that I cannot do if I use ProxySQL inside the operator. Well, I can have ProxySQL inside the operator and then ProxySQL close to the application doing all that. But honestly, from the tests I've done and from the tests we have done, that works much better with HProxy. So it's much more stable. And with ProxySQL on top of it, you can have read-write split automatically done, and then having the HProxy, which is a very strong mechanism for redirecting the incoming request, doing only that, and operator level. Finally, MySQL. MySQL. So MySQL, as I said, you need to be very careful. You need to change all the different settings in terms of buffers and buffer pool and all the other things that are proper to MySQL. But here there are also something that you need to be very careful of. Careful at. First of all, the consistency. By default, our clusters, PXE cluster, Galera cluster, comes with a WS wrap sync weight 0, which allow the node to serve still reads. You don't want that. Absolutely. In this scenario, you don't want that. Yes, you will pay a small penalty in performance, but as I've proven in another situation, please go to the Percona blog and search for that. I don't think that the small percent you waste, well, you lose in increasing the consistency, the data consistency is a waste. Or absolutely, you want to have a zero style read here, because when you are approaching the service and you have writes, you can have then the reads from the other pods, and that is important, that the data is consistent. So in this case, for instance, use WS wrap sync weight 3, and the other small thing that you should tune is the slave threads to be consistent with the amount of amount of resource you give to the pod. So if you give the pod to the equivalent of 2 CPU and having a WS rep slave threads 8, it doesn't make too much sense. Okay. And finally, this is really fine tuning, and I don't think that you should touch too much, but actually you should, in order to have a stable cluster. Again, we need to have in mind, you need to keep in mind that we are working in an environment where some hiccup could happen, some network issue could happen. And what you really want to have is to avoid to have bad surprise because some timeout in checks or is raised when it could be just waiting 1 second more and everything will be fine, right? So increase the some timeouts. There are a few parameters that I have highlighted in bold that you can eventually change, but I recommend you to discuss this with an expert. So we are here for you. Finally, backup. The backup is totally managed by the operator. You have the possibility to choose, for a scheduled backup, run on-demand backup. You can have different definition for the backup. You can actually point to different bucket, to the same bucket, different directory in order to organize your backup in a very nice way. And run scheduler backup with the scheduled feature, and plus you can have point in time. The point in time is done through block streaming, and the time between upload is as you can see 600 seconds. So and it's constantly it's pulling the bin log up to the S3 destination, and is allowing it, and the point in time recovery allow you eventually to recover up to the latest bin log that you have pushed, which is quite cool. Okay. So conclusion. We start this journey talking about why we are talking about Kubernetes, containers, microservice, because all this started from the needs from business needs, from the needs to have the possibility to scale our service to match the demands that our users are pushing on us, right? And of course, there is a discrepancy between what happened in the application development world and what happened for the databases. The discrepancy is that the many ability that you had in the application world are not directly applied in the database world when using relational database. Not because the relational database model is wrong. The relational database model is okay, is great. It's just is there to serve specific needs, and those needs are evident, in terms of data consistency and data validation. If you require that kind of system, then you need to stay on relational database model, and the relational database model will bring you some advantage, but will bring you also some limitation, and you need to be aware of those limitations. So blindly moving from what you have in as a database in your data center to container and Kubernetes without first investigating, without first doing a well-planned move, analyzing carefully how you can and what you must do, it will be really suicidal. And of course, you need to think that there is no way to have one solution for all. Okay, yes, you will have a lot of automation also doing that, but you will need to understand eventually how to split your data, how to scale your service, and so on and so forth. And why not, if that's not working with you, be ready to drop your solution and move to a different solution. Move to something that is not relational, that eventually allow you to do a better job. And keep in mind, as we said, a relational database like MySQL doesn't scale right inside a single service at the moment of writing. So what does it mean? I have one pod serving, and that pod serving writes is one pod serving writes. You cannot redirect the writes to two pods in the same cluster. Okay, that is not going to work as you expect. It's not giving you any scalability. So the maximum level of writes is the capacity you have with one single pod. Bigger is the data set, longer could be the possible downtime if you suffer about any significant problem for a pod. So that needs to be considered with, business continuity plan, RTO, FPO. This needs to be evaluated with a study. You cannot have a relation, as I said, between application and application microservice and your relational database. You will always have the need to aggregate. So, as I said, login, you cannot just have the table for the login. Well, you can, but then you extrapolate the table for the login from the schema, and it will not have validation. So, while using relational database. And if you go for sharding for sharding your data, I think you really must use an OLAP system. Nowadays, we have very good OLAP system that can work and talk with MySQL easily, like ClickHouse, and just to mention one. And it's a very good approach for you to move in that direction. So you keep your LTP agile, you keep your LTP that needs to scale a lot, light and able to scale, and then you have OLAP system that is, again, yeah, you're moving the the monolithic thing from one side to another, but at least the other one is less has less pressure right now. And again, if you are moving just to the operator for to reduce the amount of effort you require to manage your system, also ask yourself why I'm not having better automation. So if I have DevOps in my organization, is something that my DevOps can solve? If not, okay, makes sense, right? But keep in mind that you will need to move in not only to Kubernetes, not only to container, but you will have to move your approach, your data in and reorganize your data in a way that will fit that new approach. Okay, so better to check if you can solve the things in another way first, and then if not, plan it for something that is going to be serving you better. Okay, that's all for now. And if you are passionate about open source, we are hiring, and so look for us and ping Percona for Percona careers and check for the people that we are looking for, the profile we are looking. Thank you very much. And if you have questions, you can reach me directly on LinkedIn or or through Percona, and I will be more than happy to answer your questions. Thank you.